This lesson is on spontaneous processes and entropy. This will be part 4 of our thermodynamics unit. We mentioned in an earlier lesson that the first law of thermodynamics is basically the law of conservation of energy. Energy can neither be created nor destroyed in a normal chemical or physical process. So another way we could say that is that the energy of the universe is constant. Remember, spontaneous processes are processes that occur without any outside intervention. Spontaneity does not necessarily mean that it's fast or that it's slow, but just that it occurs without any outside intervention. So spontaneous processes may be fast or they may be slow. Many forms of combustion, for example, are very fast. They would occur very, very quickly and release much energy. But the conversion of diamond to graphite is actually a spontaneous process that occurs extremely at a slow rate. So spontaneous processes are just processes that occur without outside intervention. Now another factor that we need to understand when we're talking about thermodynamics besides enthalpy, our delta H, is entropy. The symbol for entropy is a capital S. Entropy is a measure of the randomness or disorder in a system. The driving force for any spontaneous process is an increase in the entropy of the universe. So an increase in the disorder in the universe. Nature tends to proceed towards states that have the highest probabilities of existing, and those happen to be those with the most disorder. Think about it. Ice, for example, which is solid state of matter, if you set it out at room temperature, it will melt without any outside intervention. It will melt and change to the liquid state, which has a higher state of disorder. And then eventually that water would evaporate at room temperature, go into the gas state, which is at an even higher state of disorder. So nature tends to proceed towards states that have the highest probabilities of existing. Those are those with the most disorder. When we talk about positional entropy, thinking about the position of the particles in the substance, the probability of occurrence of a particular state depends on the number of ways, which those are referred to as microstates, in which that arrangement can be achieved. So the entropy of a solid is less than the entropy of a liquid. And the entropy of a liquid is much, much less than the entropy of a gas. Gases have the greatest amount of positional entropy. Let's just consider what the particles, how they would be positioned relative to one another. Notice how orderly and organized the solid here is as we look at it. Remember, with a liquid, there's a definite volume but no definite shape. So the particles are able to move. There's more disorder. Consider the particles of a gas, though. They're going to be moving at a high kinetic energy, and there's going to be a lot of randomness there. So gases have a high positional entropy. Now, the second law of thermodynamics states that in any process, there's always an increase in the entropy of the universe. So the first law of thermodynamics deals with the law of conservation of energy. Energy can neither be created nor destroyed. The energy of the universe is constant. Our second law of thermodynamics deals with entropy. And it says in any spontaneous process, there is always going to be an increase in the entropy, or i.e. the disorder in the universe. So another way of saying that is that the entropy of the universe is increasing. For a given change to be spontaneous, Remember, the delta means the change in. The change in the entropy of the universe must be positive. For a given change to be spontaneous, the change in the entropy of the universe must be positive, or it must have an increasing entropy. The change in the entropy of the universe is always equivalent to the change in the entropy of the system. Remember, the system is what it is you're studying, plus the change in the entropy of its surroundings. Just like with enthalpy, there is a relationship between the surroundings and the system's entropy as well. Now here's a similar formula that we looked at with enthalpy, but it refers to entropy. Again, this is the summation formula. So when we get back to school after break, we're going to be practicing some of these, using some of these formulas. But this formula says the change in the entropy of a reaction at standard conditions, this little zero here is a superscript, means standard conditions. And standard conditions, y'all, for a gas, it means at 1 atmosphere. For temperature, is talking about 25 degrees Celsius. For the concentration, they're considered 1 molar. So standard conditions are predefined set of conditions. But the change in the entropy of a reaction is equal to the sum, this is your summation, of the moles. So you look at your coefficients in your balanced equation, the moles of the entropies of the products. And after you sum those up, you would then sum up the moles of the entropies of all the reactants, and then you would subtract them. So this is a pretty simple formula to use. You would get your entropy values off of your thermodynamic table. That's in the back of your book, and I will actually give you guys a handout that has that on it. Entropy happens to be an extensive property. So it's a function of the number of moles of the substance present. If you recall back from physical and properties can be extensive or intensive. Intensive properties were those that were independent of your amount, so your moles, but this is extensive. It does depend on the moles. So you have to look in your balanced equation and take the moles into account. Generally, the more complex the molecule is, the higher the standard entropy value is. And so if you take a look at your thermodynamic tables, you will see that the more complex the molecule is going to have a larger entropy value. The third law of thermodynamics states that the entropy of a perfect crystal at 0 Kelvin is 0. So in other words, this theoretical temperature 0 Kelvin, if you were to look at the disorder of a perfect crystal at 0 Kelvin, it is 0. This has never actually been observed. It represents the lowest possible entropy. At this point, molecular motion virtually ceases. Entropy of the substance increases with increasing temperature. Our next lesson will be on standard free energy change.